Okay, so um, we're now going to talk about linear regression. So I'm just going to write out as if I'm writing out on a blackboard and talk about these topics. Um, say we have some data, okay? X versus Y. Specifically, let's say we have n data points. Of the form xi, comma yi, okay, where I goes from 1 to n and xi and yi are real numbers, okay, for all I. So this thing, when we say xi and yi are real numbers, might sometimes be written as xi belongs to the set of real numbers and yi belongs to the set of real numbers, okay? So this symbol means set of real numbers, and this symbol means that this symbol is read as belongs to. Okay, so this whole thing is read as yi belongs to the set of real numbers. Okay, so that's useful to learn sort of math notation like this so that you can read texts that are a bit more mathematical. Let me switch colors back. Okay, so that's what we have. We have n sort of ordered pairs xi and yi, and let's make a plot that sort of is perhaps a bit representative of x and y, something like this. Okay, I'm just making up some data set, and this would be called a scatter plot of the data. Okay. Okay, so what we want to do, we want to build a simple model of the data. And when we say simple model, what we mean is that some model, some description that conveys something about the data, some truth about the data, but without necessarily giving you all the data, right? So it somehow simplifies, compresses the information contained in the data. That's what we mean by a simple model, okay? For instance, oops. Implies something that conveys information in the data, but without conveying all the data. Conveying just the data, let's say. Okay. Okay. So what's an example model? Of course, I drew this scatter plot in a suggestive manner. It looks sort of, perhaps there's a linear line that underlies this cluster of points, maybe with some noise added. So let's try that. So let's do an example model. Fit a linear relation between x and y. In other words, find a relation of the form y equals b naught plus b1x. Okay. In other words, if you're given a value of x, the prediction for y is b naught plus b1x. Okay, where b naught and b1 are also belonging to the set of real numbers. Okay, they're constants. Okay, now how to find b naught and b1? Okay. How to find it? Okay, so lots of different ways of finding b naught and b1. Good values for b naught and b1. But we will first consider something called least squares technique, or the least squares approach. Okay, sometimes also called ordinary least squares. It's called a variety of different things, but let's just have at least mention these two names for the approach. Okay, so what do we mean by least squares problem? So this is the least squares problem. Okay, for any data point, xi comma yi, given some values for b naught and b1, the error in the prediction of yi given xi is the following, right? So error equals yi minus b naught plus b1 xi. Okay, so of course this is the data, this is the prediction. You can call this data output, and this is prediction based on input xi. Okay, so we're imagining some black box that produces yi given xi, and we want to know what this function is. Okay, we are trying to say this function is approximately equal to b naught plus b1x. Okay, and then trying to find what B0 and B1 are. And that's the context in which we have this error. Okay, so this is called prediction error. Sometimes, okay, I'm going to erase this for now, but let's just call this error. Okay, now how do we find B0 and B1? We are back to this problem. We say that we find B0 and B1 in a manner that this error is as small as possible. Okay, so we define something called squared error for the ith data point. Okay, so that's of course going to be equal to that quantity, this error quantity, and then square it. No big deal. Okay, and then something you can compute is, of course, you don't want to find B0 and B1 such that the error for a particular data point is minimized. You want to sort of minimize the average error over all data points. So this quantity is called the mean squared error. Over all n data points. Is given by, basically we sum everything, all these squared errors, and divide by n, right? So this is the notation for that. Sum for I equals 1 to n, yi minus b0 plus b1 xi whole square, the whole thing divided by n, gives the mean squared error. It's the mean of all the squared errors. That's what means mean squared error. Okay, so that's called the mean squared error. Okay, sometimes we might define a quantity called root mean squared error, which of course, well, let me just define this thing. This is called mean squared error, which often is contracted as MSE, stands for mean squared error. Okay, and then sometimes people might use root mean squared error, which is that's the square of mean squared error. Okay. Okay, so what is the least squares problem? It is to find B0 and B1, which are again real valued numbers belonging to R, such that the mean squared error is minimized. And when we use the word minimized, we mean as small as possible. When we say minimized, we don't use the word minimized in the context of sort of informal English reduced, but we mean as small as possible, absolutely. Okay, that's what we mean. Okay, and of course, we saw FitLM, which solves this least squares problem. So if you say x list equals basically your x1 till xn, and y list equals y1, that's meant to be a y. Then linear model equals fit lm x list comma y list. In MATLAB gives a linear model. What we mean by linear model is y equals b naught plus b1x. Okay, so that's y is a linear function of x, and there's a constant there. That's what we mean by a linear model, because this right hand side expression is linear in the inputs. Linear model of y, output y, let's say output y in terms of input x, that's just one input, plus a constant. The plus a constant usually comes with the linearity of the model, but maybe sometimes it's worth saying that there is a constant as well. Okay, there is this constant term b naught as well. Sometimes having this constant term is called an affine model. Affine. Okay, affine is another word. Okay, so we've already seen how to use fitlm to derive a linear model, namely b naught and b1, such that this is true. In MATLAB, we already saw that lm dot, so b naught equals lm dot coefficients dot estimate of 1, and b1 equals lm dot coefficients dot estimate of 2. Okay, so that is it. We can solve this least squares problem just using this function. What we will do next is see how a function like this is constructed, right? So at least we'll see a couple of different ways of writing a function like fitlm, which helps you find linear models. And then, of course, we will generalize these methods for more complicated models and more complicated scenarios. But good to understand how things are made for this especially simple problem. Okay.